This right here is your Arizona home, and this is the inside of your house, which is always cooled by your AC. This is the outside of your house. It's always hot in here in Arizona, even if there's no sun. So all our experimentation will be based on the temperature difference from the inside of your house and the outside of your house. This right here is a Peltier-based compact cooling system. Today, we will be talking about the magic of this TEC 12706. Hi, my name is Divyam and I'm in 7th grade going to Basis Phoenix. I live in Arizona. The most necessary thing on Earth now is electricity, and 60% of that electricity is lost to heat. So what I've said is, well, why can't we take some waste heat and turn it back into electricity? And that's what we do using this thermoelectric generator. This actually is a TEC, a thermoelectric cooler. Basically, this uses the Peltier effect, which states that when electricity flows through these wires, one side gets heated and one side gets cooled. Basically, to turn it into a thermoelectric generator, you just flip the principles. You heat one side and you cool one side, creating a temperature difference, and then electricity flows out. And that is what a thermoelectric generator is. So let's say these are two different types of metal. Let's take copper and platinum, for example. They're both still good conductors because they're metals, but one is a better conductor than the other. So right here, when electrons flow through these wires, they are going through, right? So let's take this first one as copper and the second one as platinum. As it flows through, since one is a better conductor, the heat gets released. And on this one, since there's a conductivity change, it needs more energy, so it gets cooled. So that's why this part is cooled. Now, this whole area in the middle, it's the same metal, so all that heat is lost. So let's take the same thing, but let's shrink the wires or shrink the span of the pieces of metal. So let's do the same thing. So we flow electrons in. You can't see a temperature difference here. So let's take thermal imaging. So for the first little bit, the same thing happens. The Peltier effect is going on. But since they're metals, they conduct the heat. So very quickly, the whole thing gets heated, and then there goes our Peltier effect. This right here is one of the little segments inside of a TEC. As you can see here, there's a battery connected to this. This metal electrode gets electrons pushed into it, and this is an n-type semiconductor. As you can see here, it has an excess of electrons, so it's harder to flow those electrons into the n-type semiconductor. So it takes heat from all the surrounding areas, and it uses that energy to push it into this n-type semiconductor. Therefore, this metal electrode gets cooled. So now this metal bridge, compared to this n-type semiconductor, it has less electrons. So the n-type semiconductor doesn't need that much energy to push the electrons into this metal bridge. So it releases that excess energy, heating this metal bridge. So now, as you can see here, this p-type semiconductor, it has these little holes, which is pretty convenient. So the electrons can easily flow into this p-type semiconductor. So the energy that is needed to push it in here is very little. So it releases the energy, heating this metal bridge even more. So now this p-type semiconductor has its electrons, and to push it into this metal electrode, it takes energy and it pulls it in. So that's why this metal electrode gets cooled. So this is just one of the small components inside a TEC. This is an internal pellet connection. So there are hundreds of these inside a TEC. That's why one side gets heated because of this metal bridge, which is facing up or down, and these two metal electrodes, which gets cooled. That's why one side gets heated and one side gets cooled. So now let's make the magic happen. This right here is a Peltier-based compact cooling system, which does not use a compressor or any refrigerant. The only thing that's cooling it is this TEC. When we flow current through it, again, the Peltier effect is when you flow current through these wires, this side gets cooled and this side gets hot. And that's the only thing we used here. So in most mini fridges, this is basically what you use. Let's do it. So we turn this on, and then we turn on our fridge. inside here, there's only one TEC, and this metal portion right here, it's gonna get really cold, and this outside portion is getting kind of hot because of the TEC. So again, it uses the Peltier effect. One side gets heated and one side gets cooled. This metal foil part here is just to really make it a mini fridge so that the cold air gets circulated so you can cool your drinks or something. Now, when I unplugged this, I realized that some voltage was created. So basically, I thought, hmm, after I researched a little bit, I found out that that was the Seebeck effect, which basically states that once you heat one side and cool one side, there's electricity being generated. What I've done is I've taken one of these TECs, I am repurposing it to be a TEG, a thermoelectric generator. Basically, what I did was there is a heat sink right here, and I don't know if you can see it, but there's a heat sink right here is the part that will be heated. So again, I'm using this as a TEG, a thermoelectric generator. So I've put one right here. So this side is the part that gets heated, and right here is a heat sink. So this side is getting cooled. There's a temperature difference because this is the inside of your house and this is the outside. So the inside of your house is always being cooled by your AC during summer, right? This part is the cool part, and right here is a heat sink. And if you don't know what a heat sink is, it's basically a thing that takes heat and makes it go away. Basically, I'll just take this out so you can see better. There are two fans right here to help cool this heatsink even better to create even more of a temperature difference. This right here is a heating lamp, which I'm using to represent the heat source so that there is a temperature difference. So let me just turn this on right here. So this is a voltmeter, which can show the voltage that's being generated. And this is a fan that basically helps cool the TEG a little. We're going to turn on this heating lamp. Now there's going to be a temperature difference. And after a few minutes or after a few seconds, there's going to start being voltage generated. So right here, as you can see, there's 0.1 volts of electricity being generated because of this temperature difference. Now, as the temperature difference gets greater and greater, the voltage generated will get more and more. So now if we wait for a bit longer, as you can see, the voltage has gone up to 0.2 volts. Um, Unfortunately, right now the cost versus efficiency isn't great, but we're working on making that better. And in some places, like these Mars rovers here, this is the only thing you can use because you can't use solar panels in your Mars rovers because those can get dirty, they can scratch, they can get destroyed. And you can't use gas because you can run out of gas first of all, and second of all, if you have a combustion engine, it has a lot of moving parts, and that's basically what happens in your car. You don't have to take your TV to servicing, I hope, but you need to take your car to servicing every 3 months. And the Mars Perseverance rover had landed in the February of 2021. You might be wondering, well, if Mars is so cold, how do you create the heat part of the temperature difference? Well, that's where these micronuclear power generators come into play. What these mini nuclear generators do is you have small amounts of uranium in it, and it keeps doing these small nuclear reactions, which creates heat. Mars is so cold that the cold part of the temperature difference is already there. So one side gets heated and one side gets cold. Therefore, there's a temperature difference, so you get electricity being generated. That's how the rovers like the Mars Curiosity rover, which landed in the August of 2012, was able to last for so long. Fun fact, the Mars Curiosity rover was only supposed to last for 1 day. Now, if you want to know some places that these TEGs are actually used, there are some worn devices. Okay, so let's say you're using ChatGPT and you ask it what's the weather. It will give you the answer really quickly, right? But that uses about 0.34 watt hours. Let's say there's someone who uses ChatGPT throughout their day for work emails, helping their kids with homework, etc., etc. Now, let's say they use about 75 prompts. Now, let's say there's 65 of those prompts are light prompts and 10 of those prompts are heavy prompts. Now, what I mean by heavy prompts are like you send it a big PDF or a picture of a document and you ask it to summarize it or fill in the blanks or something. And what I mean by light prompts are something like what's the weather, what's the time. That adds up to about 42 watt hours a day. That's equivalent to running a 10 watt LED bulb for 10 hours. Now you might be like, well, that's not that much energy. I use 10 or 15 of those bulbs for 15 hours a day. What difference could it make? Well, all that energy is lost to heat, and we can turn that heat back into electricity, as you can see here. Right now, because of temperature difference, it's generating 0.6 watts. And there are many parts to this, like the Seebeck coefficients, the power architect overview. Now, there's also these devices that use these CEGs and that have existed in the market for over a decade. And some devices I'm talking about are like watches that are charged from your body heat and the area around you. So that's also using a CEG. This is our main power source. For any of the parts of my video, please feel free to contact me for any more information. All the parts I've used in my project will be in the video description below. And if you want any help on building this project, feel free to contact me and I'll give you a step-by-step one-on-one tutorial. Thank you for watching my video.